Welcome to this walkthrough of LeetCode problem number 2062, count vowel substrings of a string. In this problem, we aim to identify and count substrings that consist only of vowels. We'll explore the problem statement, break it down step by step, and walk through an effective solution. Let's dive in. In this problem, we are tasked with finding the number of vowel substrings in a given string word. A vowel substring is defined as a substring that consists only of vowels, specifically the characters of E, I, O, and U. However, there's an additional condition: the substring must contain each of these 5 vowels at least once. The input to the problem is a single string word composed of lowercase English letters, and the output is an integer representing the count of such vowel substrings. This means our goal is to identify and count all substrings within the string that satisfy these conditions. To better understand, let's look at some examples. In the first example, the input is word equals AEIOUU. The output is 2. The substrings that meet the criteria are AEIOU, which spans from index 0 to 4, and AEIOUU, which spans from index 0 to 5. Both substrings contain only vowels, and each of the 5 vowels appears at least once. In the second example, the input is word equals unicornarian. The output here is 0. Although this string contains vowels, it doesn't have any substring where all 5 vowels appear at least once. Now let's examine a more complex example. If the input is word equals kwayawak, the output is 7. Here, there are 7 substrings that contain all 5 vowels at least once. For instance, kwayu from index 0 to 5, and uaiuo from index 1 to 6, are 2 of the valid substrings. The explanation lists all 7 valid substrings, demonstrating how overlapping parts of the string can contribute to multiple valid vowel substrings as long as the conditions are met. This example highlights the importance of carefully considering every possible substring within the word. Finally, let's review the constraints and some edge cases. The string word has a length between 1 and 10,000 characters and consists only of lowercase English letters. As for edge cases, if the string contains no vowels, the output is 0 since no valid substrings can exist. Similarly, if the string is made up of just one vowel repeated, such as AAAA, the output is also 0 because all 5 vowels are not present. If the string contains exactly the 5 vowels in any order, like AIOU or UAA, the output is 1 because there is exactly one valid substring. Additionally, for strings with interleaved consonants, we can ignore those and focus only on contiguous sequences of vowels. These constraints and edge cases ensure that we handle all possible scenarios when solving the problem. To solve the problem of counting vowel substrings, we first consider a brute force approach. The intuition here is straightforward: generate all possible substrings of the given string and then check each substring to see if it meets the 2 criteria. Specifically, the substring must contain only vowels, and it must include all 5 vowels at least once. The steps involve iterating through all possible start and end indices to extract substrings, and then verifying if each substring satisfies these conditions. However, this method is computationally expensive. Generating all substrings already requires n² time, and checking each substring for the criteria adds another layer of complexity, making the total time complexity n³ in the worst case. While simple to implement, this approach is inefficient for longer strings, making it impractical for larger inputs where performance is critical. Now, we look at an optimized solution using the sliding window approach. The key idea here is to avoid generating all substrings explicitly. Instead, we use a sliding window to dynamically track valid substrings. A sliding window allows us to efficiently examine portions of the string while expanding and contracting the window as needed. The main observations are that a valid substring contains only vowels and must include all 5 vowels at least once. To achieve this, we use 2 pointers to represent the window boundaries. As we expand the window, we track the vowels within it using a set. If the set contains all 5 vowels, we know we've found a valid substring. Additionally, when a non-vowel is encountered, we reset the window and the vowel set. This method is significantly more efficient because sliding through the string takes n, and updating the set is O1. While the implementation is slightly more complex than brute force, the efficiency gain is substantial, making it a practical choice for large inputs. Another alternative is to use a hash map instead of a set to track vowel frequencies within the sliding window. This approach provides a finer level of control by counting the occurrences of each vowel in the window. With a hash map, we can directly verify whether all 5 vowels are present by checking the map's keys. The steps are similar to the sliding window approach, but instead of a set, we maintain a hash map to record the frequency of each vowel. If the map contains all 5 vowels, we count the substring. The overall complexity remains O(n), as we still slide through the string only once and update the hash map in constant time. While this method slightly increases memory usage, it can be useful in scenarios where tracking frequencies is necessary. However, for this particular problem, the hash map does not provide significant advantages over the set-based sliding window approach, which is why the latter is preferred for its simplicity and efficiency. The key insight to solving this problem lies in recognizing that it can be reduced to identifying substrings with very specific characteristics, substrings that contain only vowels and include all 5 vowels exactly once. By leveraging a sliding window approach and using a set to track the vowels in the current window, we streamline the process of checking for validity. This eliminates the need to repeatedly iterate over substrings and ensures an optimal balance between runtime efficiency and implementation complexity. The aha moment here is realizing that the set-based tracking simplifies the problem significantly, allowing us to focus on efficiently expanding and shrinking the window without redundant computations. This strategic use of the sliding window achieves the goal in O(n) time, making it a robust and elegant solution. To tackle the problem of counting vowel substrings that contain all 5 vowels, we start by breaking the solution into clear steps. First, we identify the problem requirements. A valid substring must contain only the vowels of E, I, O, U, and all 5 vowels must appear at least once. Our goal is to count all such substrings in the given string. While a brute force approach could generate all possible substrings and check each one for validity, this would be highly inefficient, with a time complexity of O(n) cubed. Instead, we can use an optimized sliding window approach. This method allows us to efficiently track substrings containing vowels by dynamically adjusting a window over the string and maintaining a frequency map to track the counts of each vowel within the current window. The sliding window approach begins by initializing 2 pointers, start and end, which define the boundaries of the window. We also maintain a hash map, vowel_count, to track the frequency of each vowel within this window. As we iterate through the string with the end pointer, if the current character is a vowel, it's added to the frequency map. We then check if all 5 vowels are present in the map and, if so, count all substrings starting from start to end. Next, we move the start pointer to shrink the window and remove invalid substrings by decrementing the count of the character at start in the frequency map. If a vowel's count reaches 0, it's removed from the map. This process is repeated until n traverses the entire string, ensuring that we efficiently count all valid substrings. Additionally, edge cases such as strings with no vowels, empty strings, or strings made entirely of vowels are carefully handled. The sliding window approach is highly efficient because it avoids the need to generate all possible substrings. Instead, the window dynamically adjusts to find valid substrings, reducing redundant computation. This optimization brings the time complexity down to O(n), where n is the length of the string. The frequency of vowels within the window is tracked using a hash map, which allows us to quickly check if all vowels are present. When a valid window is identified, all substrings starting from start to end are guaranteed to be valid, and we can count them directly using the formula end start plus 1. This avoids the need to iterate over each substring individually. By ensuring that non-vowel characters are handled properly, the algorithm is robust against edge cases, such as substrings that become invalid due to the presence of non-vowel characters. The algorithm relies on 2 key data structures. First, a hash map is used to track the frequency of each vowel in the current window. The keys represent the vowels of E, I, O, U, and the values store their respective counts. This allows us to efficiently check the presence of all vowels within the window. Second, the sliding window itself is implemented using 2 pointers, start and end, which dynamically adjust to define the range of the substring being analyzed. The start pointer marks the beginning of the current window, while the end pointer iterates through the string to expand the window. In terms of complexity analysis, the time complexity is O(n), because both pointers traverse the string at most once. This makes the approach highly efficient for even large input sizes. Regarding space complexity, the hash map used to track vowel frequencies operates in O1 space, as there are only 5 vowels to consider. This makes the overall space complexity constant. Now, let's look at the pseudocode implementation. We define a function, count_vowel_substrings, which takes the input string word. A set is used to define the 5 vowels, and 2 variables, start and result, are initialized to 0. A hash map, vowel_count, is created using defaultIc to store the frequency of vowels. As we iterate through the string with the end pointer, we add vowels to the map. If all 5 vowels are present in the map and their counts are non-zero, we count all substrings within the current window and increment the result. The start pointer is then adjusted to shrink the window, and any vowels removed from the window are updated in the hash map. If the count of a vowel in the hash map reaches 0, it is removed from the map. If the current character in the string is not a vowel, the hash map is cleared, and the start pointer is reset to the position after the current character. This ensures that the window only contains valid substrings. Finally, the function returns the total count of valid substrings that meet the problem's requirements. This implementation is efficient, concise, and handles edge cases such as strings with no vowels or substrings interrupted by non-vowel characters. By leveraging the sliding window technique and a hash map for vowel tracking, the algorithm achieves optimal performance with minimal overhead. This Python solution efficiently counts the number of vowel substrings in a given string word. The approach involves iterating through the string, and for each starting character, it examines substrings until it either finds all 5 vowels, a, e, I, o, u, or encounters a non-vowel character. The count vowel substrings method starts by initializing a set of vowels and variables to track the string's length and the result, count. A nested loop is employed. The outer loop iterates through each character of the string, and the inner loop builds substrings starting from the current character. Within the inner loop, a dynamic set vowel_set keeps track of encountered vowels. If the current character is a vowel, it is added to the set. If the set size reaches 5, it signifies that all vowels are present, and the count is increment. The inner loop terminates prematurely upon encountering a non-vowel character, optimizing performance by avoiding unnecessary checks. The solution efficiently handles edge cases, such as strings with no vowels or those without all 5 vowels. The time complexity is O(n) squared, in the worst case, where n is the length of the string, due to the nested loops. However, the early termination of the inner loop significantly reduces redundant operations. Overall, this implementation balances clarity and efficiency, adhering to the problem requirements while ensuring robust handling of various input scenarios. This Java implementation solves LeetCode problem number 2062, count vowel substrings of a string. The logic is equivalent to the Python solution, with adjustments for Java syntax and type declarations. A hash set is used to track unique vowels in each substring, and the outer and inner loops iterate through the string to assess substrings. The method returns the total count of valid vowel substrings. Java-specific features like hashset and arrays.asList are used to handle collections effectively. To solve this problem, we start by initializing a few key variables. First, we define a set vowels containing all the vowel characters, a, e, I, o, and u. Next, we determine the length of the input string, which in this example is 6, and initialize a variable count to 0. This variable will keep track of the number of valid vowel substrings. Now, we begin our outer loop with I equals 0, where we'll examine substrings starting from each index of the word. For each starting index, we initialize an empty set called vowel_set to keep track of the vowels we encounter in the current substring. In the inner loop, we iterate through the characters of the substring. At j equals 0, the character is a, which is a vowel, so we add it to vowel_set. The set now contains only a, so we continue. At j equals 1, we encounter e, which is also a vowel, and we add it to the set. This process continues as we encounter I, o, and finally u, each time adding the vowel to the set. When the set contains all 5 vowels, we increment the count to 1. At j equals 5, we see another u, which is already in the set, but since the set still contains all the vowels, we increment the count again to 2. We then increment the starting index I and repeat the process, but no other substrings starting from I equals 1, 2, 3, and so on contain all the vowels before duplicates occur. Thus, the final count for this example is 2. In the second example, the input word is unicorn. Once again, we initialize the vowel set, calculate the string length as 7, and set count to 0. We begin the outer loop with I equals 0, initializing an empty vowel underscore set. At j equals 0, the character is U, which is a vowel. We add it to vowel underscore set, making the set contain just U. Since the set has fewer than 5 vowels, we continue. However, at j equals 1, the character is N, which is not a vowel, so we break the inner loop and move to the next starting index. As we increment I and repeat this process, no substrings in the word unicorn contain all 5 vowels. For example, substrings starting at I equals 1, I equals 2, and so on either lack vowels entirely or encounter non-vowel characters before forming a complete vowel set. As a result, the final count remains 0, since no valid vowel substrings are found in this example. In this final example, the input word is AIOU, which is a longer string containing repeated sequences of all 5 vowels. As before, we initialize the vowel set, calculate the string length as 10, and set count to 0. When the outer loop begins with I equals 0, we start building the vowel underscore set in the inner loop. From j equals 0 to j equals 4, we sequentially add a E, I, O, and U to the set. Once all 5 vowels are present at j equals 4, we increment count to 1. As we continue, at j equals 5, the character is A, which is already a vowel, so we increment count to 2. Similarly, at j equals 6 and j equals 7, we encounter E and I, respectively, and increment the count each time. This process continues for all valid substrings, including those starting at I equals 1, I equals 2, and so on. By the end, we find a total of 15 valid substrings containing all 5 vowels in this example. Therefore, the final output is count equals 15. Here, we analyze the time complexity of the code by breaking it down into its components. First, we have the outer loop, which iterates through each starting index of the string. If the length of the string is n, this loop runs n times, contributing O(n) to the complexity. Next, for each iteration of the outer loop, the inner loop starts from the current index I and goes up to the end of the string. This means that, in the worst case, the inner loop runs n times when I is 0, and 1 times when I is 1, and so on, decreasing by 1 iteration for each subsequent value of I. When we sum up all these iterations, it forms an arithmetic series, n plus n1 plus n2 plus 1, which simplifies to n asterisk n plus 1 / 2. This gives us the total number of iterations for the nested loops, setting the stage for understanding the time complexity in greater detail. The total number of iterations derived from the nested loops is proportional to the sum of the arithmetic series, which results in O(n squared). Additionally, within the inner loop, we perform several constant time operations. Checking if a character is a vowel, adding it to a set, verifying the size of the set, and breaking the loop if a non-vowel is encountered are all O(1) operations. This means that the cost per iteration of the inner loop remains constant. When we combine the O(n squared) contribution from the nested loops with the constant cost of the operations inside the loop, the overall time complexity of the solution becomes O(n squared). Now, shifting our focus to space complexity, we analyze the memory usage of the algorithm. The main contributor to memory usage is the input string, which requires O(n) space to store. Beyond this, the vowel underscore set data structure, which holds at most 5 characters representing the vowels, uses a constant amount of space, or O(1). Other variables like count, I, j, and loop controls also require constant space. Since no additional data structures grow with the size of the input, the overall space complexity is O(n), dominated by the space needed for the input string. Now, considering different scenarios, in the best case, where there are no vowels in the string, the inner loop breaks immediately for every I, resulting in O(n) time complexity. In the average case, where vowels and non-vowels are mixed, the inner loop executes fewer iterations than in the worst case but still grows quadratically on average, maintaining an O(n squared) time complexity. In the worst case, the string consists entirely of vowels. Here, the inner loop runs the maximum number of iterations for each starting index I, leading to the O(n squared) time complexity we calculated earlier. Now, when we compare this optimized solution to a naive approach, the difference becomes clear. The naive approach generates all substrings of the input string, which requires O(n)² time, and then checks each substring for vowels, which adds another O(n) in the worst case, yielding a total time complexity of O(n)³. Our optimized solution avoids explicitly generating substrings and instead uses a sliding window approach with nested loops to dynamically check substrings, reducing the time complexity to O(n)². Finally, by analyzing the number of iterations mathematically, we confirm that the nested loops contribute O(n)² iterations, and since the inner operations are O(1), the total time complexity is O(n)². The space usage is dominated by the input string, leading to an overall space complexity of O(n). When solving this problem, several common mistakes can arise. First, it's important to handle duplicate vowels correctly. Some solutions only verify that all 5 vowels exist in a substring, but fail to ensure that each vowel is distinct. For example, a substring like AEI might be mistakenly counted as valid, even though it doesn't contain all 5 distinct vowels. Another frequent error is ignoring edge cases involving non-vowel characters. If a non-vowel character is encountered, the current substring search must be reset, as continuing could lead to incorrect counts. Efficiency is also a concern. Using a brute force approach that examines all possible substrings results in an O(n)³ time complexity, which is impractical for larger strings. Instead, optimized techniques, such as sliding windows or two-pointer methods, can be employed to improve performance. Lastly, overlooking case sensitivity can lead to errors if the input string includes uppercase vowels like AEIOU. To handle this, simply convert the input string to lowercase before processing. Another point to keep in mind is the minimum substring length required. A valid substring must be at least 5 characters long to include all vowels. Failing to account for this can result in unnecessary checks and wasted computations. To avoid this, you can safely skip any substrings shorter than length 5. On the interview side, recognizing patterns is crucial. Many substring-related problems benefit from techniques like sliding windows, so identifying when to apply such methods can significantly improve your efficiency. Additionally, always focus on the problem's constraints, such as input size, to determine whether a brute force solution is feasible or if an optimized approach is necessary. Interviewers may also test your adaptability. Be prepared to handle variations, such as case-insensitive checks or additional character sets. Finally, demonstrating an awareness of edge cases, like empty strings, strings without vowels, or those with repeated vowels, shows a thorough understanding and can leave a strong impression. This challenge shares similarities with several related problems that can help reinforce your understanding. Examples include LeetCode number 3, which focuses on finding the longest substring without repeating characters, and LeetCode number 567, which involves checking for permutations of a string within another string. Other relevant problems include LeetCode number 904, which deals with the maximum number of fruits in baskets, and LeetCode number 992, which involves counting subarrays with exactly k different integers. Alternative approaches to this problem are worth exploring as well. A brute force solution, for instance, involves checking all possible substrings to see if they contain all 5 vowels. While this method is straightforward to implement, it has a time complexity of O(n)³, making it impractical for large inputs. A more efficient alternative is the sliding window approach, which uses 2 pointers to maintain a window containing only vowels. By tracking their frequencies and validating the window when all 5 vowels are present, this method achieves a time complexity of O(n). However, it requires careful implementation to ensure the frequency checks are handled correctly. Another efficient approach is to use hash sets for tracking vowels within the current window. With this method, you add vowels to a hash set as you traverse the string, and when the set contains all 5 vowels, you increment the count. This approach is simpler in terms of logic, as it eliminates the need for frequency tracking, but it does come with slightly higher overhead due to the operations involved with managing the hash set. Both the sliding window and hash set approaches allow for O(n) time complexity, making them well suited for handling larger inputs and demonstrating a deeper understanding of algorithm optimization. To wrap up, we explored how to solve the problem using a sliding window approach, which is both efficient and effective. Remember to practice solving similar problems to strengthen your understanding of string manipulation and algorithm design. Thank you for watching, and I hope to see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!